Hello all, today we'll be discussing about DB-scan algorithm. So the full form of DB-scan is something called as density-based spatial clustering or application with noise. Don't worry about so big full form of this particular topic, but it is a very easy topic to understand in machine learning algorithm. So DB-scan algorithm is one of the most better unsupervised machine learning technique, which sometimes performs better than k-means clustering and hierarchical mean clustering. But it has its own advantages and disadvantages, which we'll be discussing at the last in this particular video. So make sure you watch this particular video till the end, because I've explained the both intuition part and the implementation part with the help of Python and sklearn, and how you can actually implement this particular algorithm. To begin with, guys, the most important thing over here is that it has four important components. One is something called as epsilon. Okay, epsilon. The second component is something called as minimum points. Then you have something called as core points. Then you have something called as border points, and you have something called as noise points. So as you know that DB-scan is an unsupervised machine learning technique. So basically an unsupervised machine learning technique, it happens in such a way that it works in such a way that whenever we have some data points populated in a particular graph, it may be 2-dimensional or 3-dimensional. What we do in unsupervised machine learning technique is that we try to make up clusters. Clusters helps you to find out the most similar points in a distribution, and based on that particular clusters, whenever a new point comes, like for the next test data, whenever I get a new data, and if I try to populate that point, whichever cluster that particular point will fall into, I'll consider that point falling into that particular group. So that is how a clustering algorithm works. I've already created videos on k-means clustering and hierarchical mean clustering. If you're interested, you can go and have a look onto that. But we'll try to understand how does density-based spatial clustering works. And this is included with noise. Okay. Now, first of all, what we do is that we will be having initial points. So this will be basically all our points. So what we do is that we initially consider some epsilon value and some minimum points value. So suppose if I'm considering over here as minimum points as 4, and suppose I say that my epsilon value is something, okay, like 3, 4, it depends on the distance. Now the epsilon value indicates very important thing. That basically indicates is that, suppose this is my point A, okay. Now what does epsilon indicates that I have to take the radius of that particular value of epsilon, okay, and then I have to create a circular path across it. That is, I have to create a circular boundary across it of that particular radius. So this is my radius, okay. Now when I create this particular radius, the next component, that is minimum points, comes into existence. Now this epsilon will be based on, like, within this point I have to minimally consider, I have to consider a minimum number of points of 4 points in this. So if I have 4 points like this, which is populated within this, then what happens is that I will be considering this point A as my core point. So very important thing to understand that to make a point considered as a core point, there should be two conditions that has to be, there should be two conditions that it has to follow. One is that I have to consider a boundary with the radius of epsilon value. Then the next thing is that I have to also consider that the minimum number of points that fall within this boundary should be less than or equal to 4 in this particular case, right? Sorry, it should be at least 4 points should be following in this particular thing, right? Or if it is greater than 4 points, it is well and good, but at least 4 points, at least 4 points should be following in this particular boundary. Then only I'll be considering this A point as my core point. So my next component that I was discussing about is something called as core point. Now there is also something called as border point. Now border point indicates something. Now suppose I have a point C, okay. Now I'll be using my epsilon value and creating my epsilon value, right? I'll be creating that radius, and with respect to that, I'll be creating my boundary. Now this particular C point, suppose it does not satisfy the minimum points is equal to 4, okay. It does not satisfy this minimum points is equal to 4, but we have at least one core point present inside this particular boundary, okay. Now just understand this, guys. Two conditions. First of all, I have drawn the boundary with the help of epsilon. The second condition is that this minimum points is not getting fixed. That basically means I don't have that many minimum number of points that I've actually initialized in this, but I have at least one core boundary inside it. So when I have this one core boundary inside it, then this points actually becomes a border points. So this point actually become a border point. Now, three things, guys. First of all, we need to understand what is epsilon. With the help of epsilon, I'm creating the boundary. Second condition is that I have to consider that minimum number of points has to be present within that boundary. Then only I'll be able to consider this point as my core point. Okay. If it is not falling, then what do is that we consider another scenario wherein we consider that at least one core point should be falling inside this boundary. If one core points basically means this kind of point. If it falls inside this boundary, then I will be considering this as my border point. Okay. Now the next thing is that suppose if I have one point like B. Now I have taken the epsilon radius. I have created my boundary. Now what if none of this is getting satisfied? If I don't have this minimum number of points as 4, and if I don't have any core points, then this point basically becomes a noise point. Noise point is basically like my outlier. Now this outlier is being very nicely handled by DB-scan algorithm. That basically means that whenever it finds an outlier, it will never draw this kind of boundary across it. So it will just skip that noise point and it will never treat it as a separate group or cluster. But whereas in the case of border point and whereas in the case of core point, it will be considering this kind of circular borders or boundaries. Or this is just like treated like a clusters. No, this is like a cluster. Now you see this. Let us see this particular example that I have. I have red points over here. You can see this. This red point basically indicates that if I'm considering an epsilon value of some value, and if I'm considering minimum points as 4, now suppose if I consider this, I've taken an epsilon length over here as my radius, I've drawn a circle. Now I'll go and see that at least 4 points are falling inside this circle. So I have 1, 2, 3, and 4. So 4 points are actually falling inside this circle. So I can consider this as my core point. So this all red points that you see is basically my core points. Okay. Now suppose tomorrow after my model is getting trained, if a new point comes over here, then this is basically treated as the point that belongs to this particular cluster where my core point is this. Similarly with respect to all the other values. But just now see about this particular yellow point. Now this yellow point, when I draw a circle around it or a boundary along it, I don't see more than 2 points over here. I have just 1 and 2, right? And this particular point, if it is considered as a core point, then this basically becomes my yellow border point. So yellow, which is my border point over here. So similarly in this case, this also becomes a border point because I have at least one core point within this particular boundary of the yellow point. Now this is how it is actually used. This whole DB-scan algorithm works in this way. It goes from one point to other. It tries to find out this particular value, whether it has that particular, it tries to create the, diameter of this particular radius that is of my epsilon value. And then what happens is that after that, it tries to then create, or try to find out the necessary core points in this by satisfying both these conditions. And then it classifies itself as a core point or a yellow border point. And wherever a yellow border point or a this yellow is basically the color, so I'm saying yellow border points. But when I see a core point, I will be trying to create a cluster. When I see a yellow point, I'll be trying to create a cluster. But whenever I find out a noisy point, I don't create a cluster. So this DB-scan algorithm works very well with the noisy points because noisy points are never taken into a cluster. So it basically skips or it does not take care of those noisy points. So DB-scan algorithm works well with the noisy point. And this was an example of this, guys. Let me just go to the next slide and show you some more things about this, like how the classification happens. In the left side of the image that you see, this grouping has been done by some other algorithm like k-means. okay, and hierarchical clustering. Okay, K means clustering and hierarchical means clustering. Whereas in the right hand side of the graph, you can see that it is this whole clusters has been happened with dbScan. This was some of the disadvantages in k-means and hierarchical mean clustering, because when our data is actually distributed, as you know that in k-mean clustering, what we do is that we may try to make clusters of points, right, based on Euclidean distance. Hierarchical mean clustering, again, there's a Euclidean distance. Again, we follow something called as, top to bottom hierarchy to actually solve that. And similarly, in dbScan algorithm, we have actually discussed about this, right? In dbScan, you can see that it has been able to group the points very nicely. And you see this. These particular points are not grouped because these all are noisy points. These are left like that. See this, these are all left like that. These are all left like that. These all points are left like that. But whereas the other point that you can see that it has been classified or grouped very nicely. So that is the advantage of dbScan algorithms. It works very well with the noisy data, right? It works well with the noisy data. Now, as we go ahead, guys, I'll also show you some of the advantages of dbScan. So it is very great at separating clusters of high density. So it focuses on high density of points because we are considering two things, that is that epsilon and the minimum points that should follow within the boundary of that. And it is very great at separating clusters of high density versus cluster of low density. And it also well defines the noisy points. And it is also great with handling outliers, which are my noisy points within the data set. Some of the disadvantages are it does not work well with dealing with clusters of varying densities, because suppose if I have some extreme density in my clusters and if I have less number of dense clusters, so all this kind of type, the dbScan will not work well. Okay, so it also struggles with high dimensionality of data, because as the number of dimension increases, it becomes very, very difficult for grouping the data altogether by using this particular density clustering. So, let us go and just understand how we can implement a dbScan algorithm, because I'm just going to show you a very good use case wherein we'll try to apply dbScan algorithm. In order to apply dbScan algorithm, guys, we will be using a library that is present inside sklearn.cluster.dbscan. So let me just go ahead. Over here, you can see that we have epsilon value, we have minimum samples, we have metric Euclidean distance, and this minimum samples is basically indicating your minimum points, and based on the Euclidean distance it can consider. Again, there are two types of metric that we can use, either Euclidean distance or we can also use Manhattan distance. It is up to you, okay, and how well it works with respect to this particular data. So let me just show you a very good example that I have for dbScan algorithm. I have a data set which is called as mall customer.csv. Okay, now let me just show you the data set. Now this particular data set, you can see that I have a lot of information like customer ID, genre or gender, sorry, it should be gender, it is written as genre. Then we have age, then we have annual income, then we have spending scope. Now what our aim should be that, I just created this problem statement that I'm going to consider annual income and spending scope. Taking these two features, I'll just apply a dbScan algorithm, and based on this density of the points, it will try to group these particular points together. Okay, so let us go ahead and try to see it. So what I have done is that I've just taken my third and fourth column, which is my annual income and spending score. So this is my third and fourth column, and I've basically used dataset oilog. So as usual, let me just open a notepad and let me just write down the steps for you all. So the first step is, as usual, let me just make the font size a little bit better and bold, 16. So let us do. The first step, as usual, is basically to import the data set. And guys, this is a unsupervised machine learning technique. So you don't have any output in this feature. You just have independent feature. And finding the similarity in the feature, what we do is that we try to, based on the density scan algorithm, we'll try to group those into clusters. Okay. So after importing the data set, we'll just, and I have my independent features over here in my X. Then I will be just applying my dbScan algorithm. Now DB scan basically, I have to import the DB scan algorithm. So as usual, DB scan algorithm is getting imported. Import the DB scan from sklearn, right? So I'll just write it down so that you will always be able to remember the steps. Now you can see that over here I've taken the DB scan, imported the DB scan from sklearn.cluster, and over here DB scan I've taken as epsilon value as 3. You know what is epsilon, with the help of which I'll be actually creating, a radius, and based on that I'll be considering epsilon as my radius and creating a boundary around that particular point. And the minimum number of samples, I'm just considering it as 4 in order to just show you how it will work. Now this is working. Now you can see that my DB scan has worked properly over here. It has got executed. Now the next thing is that I'll be fitting the model, so as usual, my third step is basically fitting the model. That basically means that my training will start over here. Now this is fine, done. As soon as I do this, after doing the fit, if I say model.labels, I'll automatically get all the labels. You can see that now my labels is like this. Now from the labels, that basically means that how many clusters or groups I'm getting it, okay? You can see that over here, there are a lot of values which will have -1. Now, can you just imagine what this -1 will be? Okay. So there are 1, zeros, -1. You can see 1 over here, 2, 3, 4, 5, 6, 7, 8, and remaining all are 1s. Okay. So 0 to 1, I have a lot of this. Understand this -1 basically indicates that these points are the outliers, okay, and they do not fall in any of the clusters. Whereas other points, you can see that it is starting from zeros, then ones, then these are basically my 0th cluster, first cluster, 2 cluster. So many groups of clusters are there. Now what I'll do is that I will try to find out how many unique groups are there. Okay, so for that, first of all, I'll just create a array by using NumPy, where I will consider everything as false. So this is the code to do that. You have everything as false right now. Then what I'll do, I'll compare this sample underscore cores and labels, and wherever these label values are true. So suppose if I just write db.core underscore sample underscore indices, this basically indicates that on which all index I'm having a different value. I'm having a different value, which is like a group, apart from -1. Okay. So what I do is that I'll take all these indexes and I'll make it as true, because this basically indicates that this many from this sample underscore core, whichever all false, remaining all are basically my groups, different groups. So you can see that all the true values are there. Then I'll just calculate the number of clusters. If I do that, I just use that length of set of labels minus this. You can see that my total number of clusters are 9. I'll not be considering -1 as my cluster, because -1 is the noisy points. The total number of cluster I had from 0 to 8. So 0 to 8 is basically my 9 clusters. These are my 9 clusters. Then I can also see my score, which is called as silhouette score, which I use it with respect to my X and labels. Based on the number of, sorry, I did not import this sklearn the metrics. And this score will be getting calculated based on the average mean of the number of points that are indicated as noisy, and when compared to the other points that are basically indicated as group cluster. Now this is a very good algorithm when you want to basically divide the data set or cluster the data set based on density. I hope you like this particular video, guys. All you have to do is that like, share, comment. Please put your valuable comments, or just like it if you like this particular video. Make sure you share this with all your friends, whoever require it. And this is how a DB scan algorithm will be done. I'll be uploading this code in my GitHub, so you can see that particular GitHub URL in the description.
이번 참조 동영상에서는 density based scan, 즉 DB 스캔에 대해서 다루었습니다. density는 EPS라고 하는 특정한 레디어스 안에 있는 점들의 숫자입니다. DB 스캔에서 포인트는 core 포인트, border 포인트, 노이즈 포인트로 나뉩니다. core 포인트는 EPS 안에 있는 min 포인트보다 같거나 큰 점들의 숫자입니다. border 포인트는 코어 포인트는 아니지만 코어 포인트 이웃에 있는 점입니다. 노이즈 포인트는 코어 포인트도 아니고 보더 포인트도 아닌 점을 의미합니다. 다음은 코어, 보더, 노이즈 포인트에 대한 예시입니다. 오른쪽에 코어 포인트를 보면 A를 중심으로 EPS만큼의 레디어스로 원을 그리면 7개의 점들이 있는 것을 볼 수 있습니다. 민 포인트가 7이기 때문에 A점은 코어 포인트에 해당됩니다. B점을 보면 A점의 근처에 있지만 자신을 중심으로 EPS의 레디어스를 그리면 민 포인트보다 포인트들이 적습니다. 따라서 B는 보더 포인트로 분류가 됩니다. C의 경우 코어도 아니고 보더도 아니기 때문에 노이즈 포인트에 속하게 됩니다. 다음은 DB 스캔의 결과입니다. 왼쪽에는 오리지널 포인트가 있고 오른쪽에는 코어 포인트가 녹색으로, 보더 포인트는 파란색으로, 노이즈 포인트는 빨간색으로 표시되어 있습니다. 여기서 EPS 레디어스는 10이고 미니멈 포인트는 4입니다. 다음은 DB 스캔을 통해서 6개의 클러스터를 성공적으로 찾아낸 경우입니다. DB 스캔은 노이즈에 레지스턴트합니다. 서로 다른 쉐입과 사이즈의 클러스터를 잘 핸들할 수 있습니다. 다음은 DB 스캔이 잘 동작하지 않는 경우입니다. 왼쪽에는 오리지널 포인트가 있고 오른쪽에는 두 가지 사례가 있는데 첫 번째는 민 포인트가 4, EPS가 9.75이고 두 번째 사례는 민 포인트가 4, EPS가 9.92입니다. EPS가 약간 변했을 뿐인데 클러스터링의 결과는 큰 차이를 보였습니다. DB 스캔은 density에 의존하기 때문에 이러한 varying density를 가지는 데이터에 취약합니다. 또한 high dimensional 데이터에서는 cross dimensionality가 존재하기 때문에 density가 작아져서 DB 스캔이 잘 동작하지 않습니다. 지난 사례에서 보듯이 DB 스캔의 결과는 EPS와 민 포인트 값에 민감하기 때문에 이를 어떻게 결정하는지에 대해서 알아보도록 하겠습니다. 기본 아이디어는 클러스터 안에 있는 포인트, 즉 코어 포인트는 K nearest neighbor과 유사한 거리라고 가정합니다. 반면에 노이즈 포인트 경우에는 Kth nearest neighbor가 먼 거리에 있다고 가정합니다. 따라서 모든 점들에 대해서 K번째 nearest neighbor까지의 거리를 구하고 이를 쇼팅하면 다음과 같은 그래프를 얻을 수 있습니다. 여기서 X축은 포인트의 개수이고 Y축은 네 번째 nearest neighbor까지의 거리를 표시합니다. X축의 포인트 개수가 증가함에 따라 Y축의 거리가 완만하게 증가하다가 급격히 증가하는 시점이 있습니다. 바로 이 지점이 코어 포인트에서 노이즈 포인트로 분류가 되는 지점입니다. EPS와 민 포인트의 역할은 코어 포인트와 노이즈 포인트를 구별하는 것이기 때문에 K값 4는 민 포인트로 지정이 되고 Y축에서 급격한 변화가 일어나는 디스턴스 9.5 내외가 EPS로 지정이 됩니다. 다음은 클러스터 밸리디티입니다. 슈퍼바이스 클래시피케이션에서 우리는 모델이 얼마나 좋은지에 대해서 accuracy, precision, recall 등의 방법으로 측정했었습니다. 클러스터 분석에서도 클러스터 결과가 얼마나 좋은지에 대한 질문을 할 수 있습니다. 그러나 문제는 클러스터라는 것은 eye of the beholder, 주관적 관점에 의해서 결정된다는 것입니다. 문제가 있음에도 클러스터를 evaluate 하는 것은 다음과 같은 이유 때문입니다. 첫째로 노이즈 안에서 클러스터링 패턴 찾는 것을 피하고자 함입니다. 두 번째로 클러스터링 알고리즘 간의 성능을 비교하고자 하는 것입니다. 세 번째로 set of clusters, 클러스터 집합이 2개 이상 있을 때 이것을 비교하고자 하는 것입니다. 네 번째로 2개의 클러스터가 있을 때 이들을 비교하고자 하는 것입니다. 다음은 랜덤 데이터에서 클러스터를 찾은 사례입니다. K-means, complete link, dbscan 모두 클러스터 결과를 지시합니다. 사실 랜덤 포인트는 노이즈에 불과하다고 할 수 있지만 클러스터링 알고리즘은 이를 구별해내지 못합니다. 이러한 문제들을 해결하기 위한 클러스터 밸리데이션의 에스펙트, 관점들입니다. 첫 번째로 클러스팅 텐던시를 결정합니다. Non-random structure가 데이터에 실제로 존재하는지를 구별해냅니다. 두 번째로 클러스터 분석의 결과를 외부에 알려진 결과와 비교합니다. 예를 들면 외부에 알려진 클래스 레이블을 사용할 수도 있습니다. 세 번째는 외부 정보를 사용하지 않고 클러스터 분석 결과가 얼마나 좋은지에 대한 평가 방법을 사용하는 것입니다. 네 번째로 두 개 이상의 클러스터 집합들이 있을 때 어떤 집합이 더 나은지를 비교하는 것입니다. 다섯 번째로 클러스터의 정확한 숫자를 결정하는 것입니다. 클러스터 밸리더티는 다음의 세 가지 타입으로 나눌 수 있습니다. External index는 외부의 클래스 레이블처럼 외부적인 정보를 활용하는 것입니다. 예를 들면 엔트로피가 이에 해당됩니다. Internal index는 외부 정보를 활용하지 않고 클러스터를 평가하는 것입니다. Sum obscured error, SSE가 이에 해당됩니다. Relative index는 두 개의 클러스터링 혹은 클러스터를 비교하는 것인데 External index나 Internal index를 사용할 수 있습니다. 어떤 경우에는 index란 말보다 criterion, 기준이란 말을 사용하기도 합니다. 클러스터 밸리더티를 correlation을 통해서 측정할 수 있습니다. 아래에는 두 개의 K-means 클러스터링의 결과가 나와 있는데 왼쪽에는 correlation이 -0.923으로 -1에 가깝습니다. 오른쪽은 -0.5851이 나와서 0과 1 사이에 중간 정도에 있습니다. 코릴레이션의 절대값이 1에 가까울수록 강한 상관관계가 있고 0에 가까울수록 랜덤에 가깝기 때문에 우리는 왼쪽의 K-means가 클러스터 밸리더티가 더 높다고 할 수 있습니다. 다음 사례는 클러스터 밸리데이션을 위해서 시밀러리티 매트릭스를 사용한 경우입니다. 오른쪽 그림은 시밀러리티 매트릭스를 색으로 표현하고 있는데 빨간색으로 갈수록 시밀러리티가 높은 것이고 파란색으로 갈수록 시밀러리티가 낮은 것입니다. 빨간색에 3개의 박스가 있는데 그것은 각 클러스터 안에서 시밀러리티가 매우 높다는 것을 표현하고 있습니다. 다음은 랜덤 데이터를 DB 스캔을 통해서 클러스터링을 한 결과입니다. 시밀러리티 매트릭스에서 3개의 빨간색의 박스를 볼 수 있지만 색깔이 크리스프하지 않은 것을 볼 수 있습니다. 즉, 시밀러리티가 높지 않기 때문에 클러스터 밸리데이션이 약하다고 볼 수 있습니다. 이번에는 랜덤 데이터를 K-means로 클러스터링한 결과입니다. 비록 DB 스캔보다는 빨간색들이 좀 더 많이 보이지만 여전히 사각형의 윤곽이 크리스프하지 않은 것을 볼 수 있습니다. 컴플리트 링크로 랜덤 데이터를 클러스터링한 것도 결과가 크리스프하지 않은 것을 볼 수 있습니다. 클러스터 밸리더티에 대한 파이널 코멘트입니다. 클러스터링 스트럭처에 대한 밸리데이션은 가장 어렵고 힘든 분야입니다. Without a strong effort in this direction, 이 방향으로의 강한 연구가 없으면 Cluster analysis will remain a black art. 클러스터 분석은 black art, 주술로만 남을 것입니다. Accessible only to those true believers. 그것을 진정으로 믿는 사람들만 할 수 있을 것입니다. Who have experience and great courage. 경험과 용기를 가진 신봉자들만을 위한 것입니다.